The Blin-Fong reflection model has been around for more than 30 years. It used to be hard-coded into older GPUs from the early 2000s. It's easy to evaluate and somewhat intuitive to control. One technique worth mentioning with this reflection model is that you can give the specular highlight a different color than the diffuse components. For example, if the specular component is given a white color, the object looks more like a shiny plastic. If both the specular and diffuse components are multiplied by the same color, the material looks more metallic. However, this classic reflection model is not energy balanced. You'll notice as I change the shininess that the material looks smoother, but overall the amount of light reflected becomes greater. If you think about it, this makes a lot of sense. Here's the Blin-Fong equation again. You take n dot h and take the maximum between that and 0, and then raise that to the power shininess. The graph of the angle between n and h versus the specular intensity is like this. Clearly the area under the graph for cosine squared is smaller than for cosine, so the amount of energy coming from the surface will be less as you increase the shininess. Cosine cubed has even less overall energy. As the shininess goes up, the area under the curve goes down. Two changes give a better result, one that's both more plausible and easier to control. One idea is to attenuate the specular term by the Lambertian falloff. In other words, just like diffuse, make the specular term drop off as the angle of the light to the surface becomes less straight on, n dot l. The other idea is to make these narrower curves be higher, giving them roughly the same volume in 3D. This idea is captured in the last term. As shininess increases, this last term also increases. When combined with the Lambertian term, this new equation gives a reasonably balanced result. Here's the original Blin-Fong equation. You can see with a shininess of 3, it's overall much brighter than a shininess of 100. By energy balanced, I mean that changing the shininess does not noticeably change the amount of energy reflected from the surface. You can see the effect by running the demo that follows. By the way, this demo puts all its shaders inside the JavaScript program itself, if you want to look at an example of how that's done. Using the Lambertian n.l term also eliminates a serious problem with specular falloff. You may have noticed it yourself with the basic Blin-Fong model. Here's a view of the model with the low shininess and the light coming up from behind it. The diffuse term drops off smoothly, but the specular suddenly drops to 0, giving a pretty bad result. By using the Lambertian drop-off, the specular term now fades properly.